Great. So today we have Joseph Jensen. He's a PhD student at the University of British Columbia as our speaker. He will be discussing ultra-marginal feature importance, learning from data with causal guarantees. So welcome, Joseph, and yeah, the floor is all yours.
You have to enable screen sharing, looks like.
Okay, yes, now.
Okay, so yeah, I'm going to be talking about my recent feature importance paper that was published last year in AI Stats. This was work done with my colleague Vincent Guan and my co-supervisor Elena Robiva as part of the Institute of Applied Math here at UBC. So feature importance is a really broad topic, and because of that, it can answer many different, totally independent questions. So you might want to know which features should I delete during the feature selection phase of my modeling pipeline, which features are causing changes in my response, which features are most associated with my response, which features are disproportionately altering this particular prediction, or even which features are primarily affecting my model performance. So all of these questions can kind of be fit into four categories based on like what their motivation or goal is. So the first category, and really the most popular, as you see in the table below, is the global model framework, where we want to gain an understanding of an entire model. And then we have a local model framework. Examples of this include like SHAP and LIME, where we want to understand a particular prediction that we're making. Then there's a global data framework where we want to gain an understanding of an entire data set. And then the local data framework where we want to gain an understanding of a particular prediction. So you'll notice here that most work has really focused on the model framework because, people in machine learning, method development care about models. They're not they're not applied scientists, so they don't have the idea to focus more on learning from data. Rather, they're trying to interpret a model or trying to optimize some model. But this motivation of machine learning developers is in stark contrast to people who actually use feature importance. So Christoph Molnar, who you may know of from his popular feature importance textbook, ran a poll on Twitter and saw that 35% of users of machine learning interpretability want to get insights about data, even though these methods are not made to get insights about data. So this mismatch between the motivations is clear also for scientists and method development and the methods currently in development. So I like this quote from Roscher et al. In 2020, who summarizes the motivation of scientists as utilizing ML. The main goals for utilizing ML are scientific understanding, inferring causal relationships from observational data, or even achieving new scientific insights. So all these papers in really high impact journals kind of claim that this is their goal, but they are using feature importance methods that are strictly made to interpret a model or to optimize some model. So there's a huge mismatch here. Now, to resolve this mismatch, the first method that was developed specifically for scientists who want to understand and infer relationships from observational data came from Katav et al., published in ICML, who developed marginal contribution feature importance. So they developed it to satisfy three axioms. The first is marginal contribution, second elimination, third minimalism. And they proved that the only feature importance method that satisfies these three axioms is what's given in equation 1 here. So the importance of xi is given by the maximum over all subsets of the feature set of the universal predictive power nu of S and xi minus just the universal predictive power of S. So again, this is maximized over all subsets of the feature set S. One way you can think about this universal predictive power is just replacing it with mutual information. And in practice, we would replace nu with some machine learning algorithm and estimate the test set R squared or something like that. Now, cracks began to form in this method, even in the original MCI paper, marginal contribution feature importance paper. So they test their method on a bunch of genes and how they relate to breast cancer. And they found that all genes had significant importance. So even the gray genes here, which are supposedly not related to breast cancer, are given some high importance. So even before we started this, we suspected that MCI sometimes gives too much importance to unimportant variables. And this really comes from this maximum overall subset. So you're bound to get something much larger than 0. The next issues that I found with this method came from when I tried to apply this to hydrology. So I
Sorry,
wanted
Joseph.
yeah.
If you don't mind, could you go back to the definition?
Yeah.
And in order to not get lost, if you don't mind, it would help if you could give a little example where you give an example of feature set, what is xi,
Yeah.
and so
So
on, just so I can put it in context. Yeah.
Yeah, you can think of F as the CAMEL's catchment attribute data set. So you have a bunch of climate attributes, a bunch of vegetation indices, and some topographic geological indices, etc.
Okay.
So now you're going to subset them. You're going to take a subset of them, and that's
When you say
F.
subset them, you're not subsetting on, you're subsetting on features as opposed to like in random forest where you subset on number or values, right? You're
Right.
subsetting
You're
only on
not subsetting observations, you're subsetting in the feature space. Yeah.
Okay.
So you take a subset of features, and then xi, let's say that's mean annual precipitation. So you calculate nu, which could be, let's say, the outer bag R squared of random forests, given the feature set S and mean annual precipitation, and then you subtract that from the outer bag R squared of just random forest just given S. So you have two models.
So xi is not contained in S.
No, it can be, but it doesn't matter because it's a maximum. And if xi is in S, then it's just going to be 0. Right? So.
Okay.
Okay, so we tried to use MCI to explain what catchment characteristics are most associated with streamflow characteristics, i.e. the CAMEL's data set, the CAMEL's kind of spatial data set, not the time series. And we found that MCI is way too computationally expensive, so we have to evaluate 2 to the p model trainings, where p is the number of features. So we were basically limited to like less than 30 features, even though CAMEL's has maybe like 40 or 50 or something.
And again, just to stay up with you. So
Mhm.
S can be as little as one feature and as
Yes.
large as all the features.
Yeah.
And that's what you're trying to do here. You're trying to see when you add one feature to some small subset, does it make any difference? And you're trying to search over all possible combinations of features.
Exactly. Yeah. Mhm.
Okay, now it makes sense. Okay.
And we also found that MCI detects too few interactions. So at least I would expect hydrology data sets to have really crazy interactions. You know, everything should be somewhat interacting together. But we consistently observe that MCI chose at the size of S to be less than 3. So that's not allowing for many interactions to be detected. So we can have an illustrative example of this. So one example from hydrology could come from temperature and precipitation, where we would expect them to be spatially correlated, but they can also interact. So together, they can provide more information about stream flow than can be seen when considering them individually. So if we have this simple experimental setup of y being x1 plus x2 plus an interaction term, sine of x1 times x2 plus x3 plus x4, we would expect, due to this extra interaction term, that x1 and x2 are more important than x3 and x4. We can see in the first plot then when x1 and x2 are independent, we do get this result, so it's a nice result. But in the second plot, x1 and x2 are strongly correlated. And we can see here that MCI gives the exact same feature importance for all features. So this is because in their formulation, dependence and interactions are fighting against each other. I think, some of the talks, some of the papers in hydrology and some of the talks I think I've seen here have kind of addressed this a little bit, but this is a very clear example of how we can see this. So the objectives that we have for a new method, if we were to create one, would be, can we tailor some method to scientists with a special emphasis on hydrologists who want to understand the strengths of complex associations in a data set? And is it possible to develop a feature importance method that doesn't treat dependence and interactions as a trade-off? So can we detect correlated interactions? And also, can we satisfy this goal while becoming computationally efficient? So it turns out that the problem that I just laid out is actually basically completely solved by previous literature in AI fairness. So our goal for this feature importance method is that given a feature set F and a feature of interest Xi, we want to find some representation of the data, S, that is independent of Xi, while keeping as much of the information from F as possible. So this independence of Xi allows us to kind of remove all these correlations that interfere with interactions. And this keeping the original amount of information allows us to keep all those, to keep the ability to detect all those interactions. Now, the goal of AI fairness is
Sorry,
to,
Joseph.
yeah. Mhm.
So SF of Xi is the representation of F when Xi is not included?
It's more than just not included. It's the entire feature set is transformed such that it's independent of Xi. So before you can predict
Each feature is independent of Xi. Is that when you say it's independent, that means every individual feature has to be independent of
jointly independent. Yeah.
I'm having trouble understanding
this can be a feature set. And yeah, we'll discuss this later, but it's going to be the entire feature set is independent of xi. So the goal of AI fairness is to pre-process a set of features by finding a fair representation of the data that is independent of some sensitive attribute like race, age, or gender, while maximizing predictive performance. And actually a similar concept is found in privacy, where you want to optimize some privacy utility trade-off as well. So we're going to use these methods from AI fairness and privacy, namely linear regression and optimal transport, to find a new preprocessed feature set S that ideally obeys 3 properties. So these 3 properties define what it means for some feature set to be preprocessed optimally. So first, we don't want any extra information in the data set. So basically, S should be some deterministic function of F, basically by the data processing inequality. Second, we want our new representation to be independent of xi, of the feature of interest. And we don't want any information loss. So we want the mutual information of the original data set to be the same as the preprocessed data set and xi. So no information loss. So now with this, we can introduce our new feature importance method, ultra-marginal feature importance. So given a response y and a feature set f and a variable of interest xi, UMFI is defined as this. So the feature importance of the feature xi is given as the universal predictive power of S and xi minus the universal predictive power of S. And in our definition, we assume that it satisfies the optimality conditions of the preprocessed feature set up here. So basically, in the algorithm for UMFI, we have a response and a set of predictors, and also we choose a single feature. And based on that, we obtain S using a technique that optimally removes the dependencies on xi from F. Then we specify some method and evaluation function. And then we just estimate the predictive powers of just the feature set S and estimate the predictive power of the feature set S plus xi, and then we just subtract them. So it's very simple. Now, in practice, how do we remove these dependencies? So the first kind of simplest method is linear regression. Basically, the idea is to use the residuals of linear regression to obtain from regressing the feature set on the feature of interest. And this turns out to be optimal when everything's multivariate Gaussian. So we basically set S to be defined as the residuals resulting from xj. So that's one of the features in F that's not xi, minus beta 0j minus beta 1j xi. So xi is the feature of interest, and it's always being used to predict xj. So these residuals, if it's multivariate Gaussian, will be independent of xi. They're automatically have 0 covariance with xi, but when it's multivariate Gaussian, it's also independent. The second method comes directly from the fairness literature, Jandro and Lum. So they use optimal transport. Basically, the idea of optimal transport is you have some distribution and you want to transform this distribution to be independent of xi while minimizing the kind of transportation cost. So in our case, the transportation cost is minimizing this information loss with respect to xj. So optimal transport is a bit more complicated than linear regression, and we'd expect it to work a bit better for discrete and more complex distributions. And yeah, basically the algorithm for optimal transport is just given basically by the inverse, by the conditional CDF of the feature given the feature of interest. So first, I just want to show that linear regression is indeed optimal under Gaussianity. So basically, to prove that linear regression is optimal, all we have to show is that it satisfies these three conditions. So the first condition, no extra information, is satisfied automatically because S is just a deterministic function of F by construction. The second one, which is that S should be independent of xi, is satisfied just because automatically the covariance of S and xi is 0, and S can be expressed as a linear transform on F. Hence the transform feature set is still jointly normal, and then the covariance equal to 0 implies that S is actually independent of xi. And finally, we want to prove that there's no information loss. So these two mutual informations are equal. And this is proven by the fact that basically the data processing inequality, it suffices to show that this transform matrix that we're imposing on F is bijective. And it is because A turns out to be invertible. Okay, so we kind of, before we laid out some broad goals for what we want our feature importance to satisfy, but we also want to have some like more rigorously defined mathematical goals. So the first important axiom that we have is the elimination axiom. So we want our feature importance method to satisfy the fact that eliminating a feature X can only decrease the importance of other features. So maybe a better way of thinking of this is the opposite. So if you add a feature to your data set, these extra correlations that might be there can't corrupt the other importance values that you've already calculated, but you could be introducing some extra interaction terms that you couldn't detect before. Then we have the invariance under redundant information and symmetry under duplication axiom. So that's basically if we add some redundant feature that only contains redundant information, then we're not changing the importance of any of the pre-existing features in F. And also if we add a completely duplicate feature, so if it's a if some feature that you're adding is a bijective function of a feature that's already in the feature set, then those two features should be given equal importance. And the last one, which is maybe the most interesting and important, is the blood relation axiom. So if there is some true causal graph, it doesn't have to be known at all. It just suppose there's some graph G. We should only be giving non-zero importance to a feature if it's blood related to the response Y. So yeah, so an example is given in this graph where S is an unobserved confounder between Y and X3, and the blood relatives of Y are given in red. So in this case, we should only detect that X3 and X4 are given positive importance, while X2 and X1 are given zero importance. Again, S is unobserved. So more specifically, we define a blood relative in the same way as you would in a family tree. So basically, we look at Y, and if it's an ancestor of Y or a descendant of Y, then it's a blood relative. And also, if it shares a common ancestor, then it's also a blood relative. So basically, our main result, or our main theoretical result of the paper is showing that UMFI satisfies the three axioms that I just outlined in the case of multivariate Gaussian distribution. So I won't go over the full proofs because they're pretty long, but for the elimination axiom, it basically just follows from the fact that mutual information has this supermodularity property when S is independent of Xi. The redundance and duplication axiom is proved basically by showing that the equivalence classes S with the normal feature set and then S with the augmented feature set are the same. And then the blood relation axiom is shown by, well, basically you need the faithfulness assumption on the causal graph, and the fact that we have this conditional independence implies independence in the case of Gaussians. Okay, yeah, so these are the full proofs. I'll just skip these. Yeah, we also had some other theorems in the paper, assuming Gaussian is kind of restrictive, so we wanted to move away from that. It turns out that the redundant information invariance axiom is true for UMFI more generally, which is nice. The elimination axiom is satisfied automatically when we use a certain type of pre-processing algorithm to remove dependencies. For the blood relation axiom, all you really need is faithfulness of the original causal graph and the new causal graph. And if you're familiar with partial information decomposition, I know that's popular in hydrology. If we don't have any interaction information, then, or synergistic information, then the blood relation axiom is also true. So now we get down to our experiments. The first experiment is super simple. It's just we have 4 features in our feature set, all normally distributed, and there's just one nonlinear interaction term for x1 and x2. So we would expect x1 and x2 to be more important than x3 and x4. And indeed, all of the methods that we compared satisfied this. So the first method we compared is the ablation. Basically, it's measuring the difference in predictive performance of the model trained on the full feature set versus the model trained on the feature set minus the feature that you're trying to measure importance on. Then there's conditional permutation importance and permutation importance. These are like the most popular methods. And then we have MCI, which is the one that we based our method on, that we criticized, and our two methods, Umify with linear regression and Umify with optimal transport, are given on the far right here. So next we have the correlated interaction experiments. This is the one I showed in the beginning of the presentation where MCI fails, and we see that MCI is the only one that fails out of all the methods. But we'll see some differences in the next experiment. So this correlation experiment is really what differentiates models that are for understanding data, which are on the right-hand side, and models that are for understanding or optimizing a model, which are on the right-hand side. So we have 3 independent features, all normally distributed, and then one feature x3 that is highly correlated with x1. And then y is just x1 plus x2. So when you're trying to optimize a model or like select features, you might want to choose ablation or CPI as your method. And indeed, in this case, it kind of shows that you can kind of delete. I mean, yeah, normally you would do this in an iterative fashion, so this is why the results look kind of weird. But in this case, it's only showing that x2 is important because x1 is already contained in x3, and x3 is kind of contained in x1. So it's really trying to remove x1 and x3 because it sees them as not adding any information. So for permutation importance, you might use it to understand a model. And indeed, in random forests, when you add a redundant feature, it's going to kind of randomly choose between one or the other with no care about kind of the data set. It's just going to randomly choose. So when you add a redundant feature, it's going to decrease the importance of all the correlated features. So indeed, you see that x1 and x3 are less important than x2, even though in the original equation, x1 and x2 are kind of equal there. So now MCI as well as our methods successfully detect that x1, x2, x3 are all strongly associated with y,
Joseph.
as you would want.
Joseph.
Mm-hmm.
If you change the equation y is just x2,
Mm-hmm.
then x1, x3, and x4 should show no importance, and x2 should be high.
Mm-hmm.
So it's not clear to me how adding x3 is equal to x1 plus epsilon actually does anything other than you're testing for some kind of numerical stability in this algorithm.
Yeah, I mean, so adding x3 to your data set basically will decrease the importance of other feature importance methods that kind of detect some sort of correlation. So in ablation and CPI, they're severely punishing correlated features because in feature selection, you don't need correlated features. You can just delete either x3 or x1. It doesn't matter, right? In PI, random forest just kind of randomly chooses either x3 or x1, and PI is properly kind of detecting the use of those features within the random forest model.
Okay.
And then MCI, UMFI just care about the associations in the data set. So adding X3 doesn't change the associations between X1 and Y. So, you know, the feature importance stays the same.
Okay.
Well, I should mention that this property may seem kind of silly, like we're just including some small noise term plus X1, and we're defining an extra feature based on that. But this actually comes up a lot in hydrology. So we have, you know, for example, hydraulic conductivities on different layers of the soil, which could be correlated with 0.98 or something. We have kind of minimum, maximum, mean temperature often in our data set. And just because we're including 3 different temperature features doesn't mean those temperature features should be punished because of that. So whether or not we only have mean temperature or we have mean, max, and mean temperature in our data set, it doesn't change the associations between those temperature features and Y. So the importance methods on the left will change those values when you include more and more temperature variables, but MCI and UMFI will stay stable and show you those true associations. Okay, so next we have the blood relation experiment. So we kind of developed a complex data set based on this causal graph, and we see that ablation, CPI, and PI all give kind of strong importance to X2, X3, X4, even though X2 has no relation with Y. Okay. And in the blood relation experiment for MCI versus UMFI, we see that MCI again gives some importance to X2, but UMFI gives 0 importance. So UMFI only gives importance to X3 and X4, since they are blood related. Now this breast cancer data association data set is the most common kind of a benchmark for feature importance methods. So we tested on this. MCI, as we saw before, can kind of give a lot of importance to unimportant features. So these genes are not associated with breast cancer. And further, we kind of randomly permute them, these features, so they're definitely not associated with breast cancer. We find that MCI gives the correct ordering, but can kind of give large importance to unimportant features, while UMFI always shows that the unimportant features are actually 0, which is cool. And surprisingly, we were able to kind of improve this method while having a really nice time complexity. So MCI is crazy expensive. You can only do like 30 features because it's O to the P, but UMFI is only OP. Yeah, it's approximately superlinear, a bit less than P squared, so it's nice.
What method are you using for the representational transform? The Gaussian method or the...
Yeah, so the light blue line is optimal transport, and then UMFI, the dark blue is linear regression. So we show both there. Optimal transport is, yeah, obviously a bit more expensive. So in conclusion, MCI, which is the method that we improved upon, is a really powerful method for science-inspired feature importance, but it has major drawbacks. First, it's computationally expensive. Second, it fails to detect interactions when they're involved among highly correlated features, which we experience a lot in hydrology. And third, sometimes unrelated features are given high importance. So UMFI greatly improves upon all these downsides by incorporating dependency removal techniques from the AI fairness literature. And future work, we want to kind of consider other dependency removal techniques like optimal transport with chaining, this thing called principal inertial components, and also neural network optimization. Yeah, we kind of want to see how the graph changes, the causal graph changes, and the properties of this causal graph when we modify the variables, when we get our new kind of fair representation of the data. And third, which I find most exciting, and let me know if you want to work on this together, I'd like to extend UMFI to a local data case. So I want to see what influenced a particular observation the most. Yeah, so we have an R package and a Python package for this if you want to use it, and I'll take any questions.
Thanks, Joseph. Could you clarify that last point about what influenced a particular observation most with an example?
Yeah, so let's say we have so we're looking at the camels spatial data set with catchment attributes and hydrological signatures. Suppose we observe some catchment with kind of extremely high base flow index. And we want to determine kind of what caused that particularly high base flow index. So is it maybe snowmelt or hydraulic conductivity? So in the regular UMFI case and the global data case, we're looking at the entire data set and associations in the entire data set. But in the local data case, we want to look at a specific observation and see kind of why that particular observation is the way it is. In a similar sense, that we have SHAP and Lyme, but those are for explaining a particular prediction, but perhaps we can do it for an observation.
When you're going from F to SF, is the dimensionality changing or is it remaining the same?
So yeah, it's changing only because we're basically just removing xi. So
for example,
we're including all xj.
Okay.
That's in the future set minus xi. So it's just reducing by 1. Right.
I'm just thinking of the case where you have x1 and x3 correlated to 0.999, some very high value. Essentially, you're doing a kind of a coordinate rotation, right? So you're redefining your new variables in terms of some coordinate rotation so that something is independent of them. But I'm curious how if we took the original set of xi's, the f, and you did an auto-encoding of f, where you reduced it to the smallest number of dimensions of variables, which does not lose information in the information bottleneck sense, right? So if you think of it as a dimensionality reduction, such that all of the relevant information about y is still preserved in SF, right? But SF could in principle be a compression of F.
Yeah.
I'm wondering how that would relate to this this methodology you're talking about, because it seems to me it still preserves the criteria that you wanted, which was that all the information is preserved, and well, I'm not sure it preserves all of them. Oh yeah, no extra information. I'm not sure about the independence of the feature of interest, but no information loss for certain.
Yeah.
Sure.
I mean, I'd say the second property is basically the most important. So we want to get that feature set to be independent. And people in AI fairness, I think, have used autoencoders.
Okay.
It's a bit more complicated, so you have to kind of make this criteria kind of convex and differentiable or something. And yeah, I haven't tried it, but yeah, that's kind of one of the things in future work. We want to basically use some autoencoder to create this representation.
Because I think you'd probably have to do it many times. You can define the encoded layer, the compression, such that the variables are independent of each other, maximally independent of each other. And in this case, you would have to preserve one of those variables to be the original variable xi. So you couldn't change that. That would have to remain, and then the remaining ones would have to be some kind of
exactly
encoding. Then you wouldn't need to make these assumptions about Gaussianity or discreteness or whatever.
Yeah. I mean, in general, the optimal transport works pretty well, but yeah, there's definitely some improvements that can be made with neural networks, probably.
Just curious, yeah.
So actually, the optimal transport works perfectly well on the gene data set that I showed. But we tried on the camels data set. It works pretty well, but we can tell it's not optimal. So it's not quite satisfying this second kind of axiom here, where we want full independence. So
didn't you also say that you needed the variables to be discrete? Or
you don't need so for optimal transport, you don't need it to be discrete. It works better when it's discrete or some complex distribution like I don't know, gamma or something. So
I see.
Yeah.
So in your linear regression case where you're assuming multivariate Gaussianity, I guess implicit in that statement is that all the variables, they can only have linear relationships. They can't have nonlinear relationships. Am I understanding that?
I mean, I see what you're saying, but I think it doesn't matter. Like if it's nonlinear, it might not be Gaussian anymore.
So it's implicit. Yeah, okay.
Yeah.
I was trying to just wrap my head around if I had missed some other step. Like if at one point you mentioned adding like a bijection to like make to linearize things, but I think I misunderstood. I think that's all implicit in the assumption.
Yeah. Because when it's multivariate Gaussian, the bijective kind of linear linear matrix transform is optimal in the sense that it obeys all these properties. So we didn't assume anything about the relationships, just multivariate Gaussian.
And then I'm going to pick on one thing in your because in your first response to Hoshin, initially you said causally, and in other instances you've said you've used the word associated.
Yeah.
And so I think you mean associated, but with the correct sort of directionality of the relationship, but not necessarily causal drivers. Is that right?
Right. So I think you're talking about
The blood DAG as well. I mean,
okay, blood thing, or are you also talking about the local data case, or
well, let's use the blood DAG.
right?
So like
Right. So the causal, so the title here with the causal guarantees doesn't necessarily mean we're detecting only the parents of Y. It just basically means that, given some data set that comes from a graph that can be unknown, we can like guarantee that we're only getting non-zero importance values for some specific subset of this causal graph, namely the blood relatives. And actually, I think Pearl and a bunch of papers mentioned that this blood relative thing is exactly the definition of association in the causal graph. So they don't mention blood relative, but they do say is a descendant or a common or an ancestor or a shares a common ancestor, and that's the definition of association.
Okay.
So association is exactly blood relative in our case.
Yeah, I see what you're saying. I think I'm conflating this spurious correlation. Like, depending on what you're doing, X2 could be spuriously correlated. But I retract my statement. That was clarifying. Thank you.
Yeah, actually, X2 is not spuriously correlated or correlated at all. It's just that X2 helps to remove some of the noise of X3 to improve your predictions of Y. So, you can improve the predictions of Y, but it's not at all related to Y.
So if you're predicting Y,
mm-hmm.
and you condition on X3 and X2, would not X2 appear to be correlated? Because I know I don't want to distract too much.
No. Condition on X3, it's correlated, yes, but X2 is not correlated with Y or dependent on Y in any sense.
Right. And you set me straight. So I kind of understand now what you mean by associated.
Yeah. And just one quick comment about that. This is important because many times in hydrology, we don't have these direct parents or whatever. We have these kind of proxy variables that could be coming from some unobserved confounder or whatever. We have these sets of snow variables kind of all representing the same thing, or sets of temperature variables, and we always want kind of all of them to show some importance. So that's why we do this. Dan?
Yeah, thanks. Really interesting. I have a question about the you're talking about minimizing information loss in the transformation. And I guess I'm wondering what is the information loss a result of? Is it like the nature of the distribution, or where does that come from?
Well, so if you just want to satisfy these two axioms or properties or whatever, what you can do is just replace F with all zeros, right? So if all your predictors are just a bunch of constants, then it's independent of xi and it's some function, deterministic function. Well, yeah, deterministic function. But you have this crazy information loss. So this is just kind of to prevent that, basically, and you can kind of interpolate from that extreme case to the ideal case, right?
Okay, so
But you're
so then
asking more in practice where it comes from, or like,
yeah, like some of it comes from the choice of transformation, and then would some of it come from just the nature of the like the distributions of the individual features, or
yeah, I don't think it's nature and the distribution, because I mean, I don't know this, we didn't prove it, but I have a feeling that satisfying all these properties is always possible in theory, at least. But we have, you know, these imperfect methods for doing it. So, for example, where is it? In optimal transport, we need to approximate this conditional CDF, which is, not possible to do super easily. And you'll also notice that in both of these cases, linear regression and optimal transport, we're considering each variable separately. So we look at xi and then xj, and then we look at all other pairs. So xi, xp, xi, xl, whatever, right? So it's not removing information that, like interactive information. So if the information is only available, if the information for predicting xi is only available in two features, so there's some synergistic effects, then we can't remove those dependencies. We can only, well, we can in theory, but just not using these two methods that we use. So there's also this optimal transport with chaining, which supposedly can remove those synergistic effects, but it's a lot more computationally expensive, and we just never implemented it. So especially because we have these, like, we would have these high order conditional CDFs that we'd have to estimate, which is just a pain. So we didn't go there.
yeah, so like this I guess really focuses on like I again I'm also really rooted in how highly correlated all of these catchment attributes are. And I guess all the interactions as well. And then I guess the other side of that, and I'm wondering how this fits in with the other side of the attributes problem being sensitivity to like the measurement uncertainty. Is this do you see a role for
I mean,
this?
I think all methods will have, a huge amount of sensitivity to this. So like if you keep adding noise to one of your features, it's going to decrease in importance, right? This is kind of maybe a good thing within machine learning, because machine learning can rely less on really uncertain features like hydraulic conductivity and focus on things we know, like climate. If you really want to use things that are uncertain, then you can just go to physically based models, I guess. Right?
All right, thanks very much.
Yeah. Ocean again?
Sort of a perhaps naive but and slightly tangential question, but it's based on something I've been trying to think about over the last few months. And that is this issue of context dependence. I could be wrong. You guys know more about this than me, but most of these explainable AI methods or explainability methods or sort of sensitivity methods, basically, where the implication is that
But you said sensitivity methods?
yes, you're testing, when you say importance, another broad term for importance is sensitivity, in the sense that you're saying that if you change something, then it has an impact on so the variable has an impact. One of the ways you detect it is by checking if you change that variable or you drop it out, whether the thing you're interested about.
I mean, that's true for the model-based feature importances, but I would argue that it's not really true for MCI and UMFI. So
okay, so if you could hold a minute, we could go there. So I'm thinking of, I'm trying to come up with a very naive example which might help illustrate my question. But let's say I have a streamflow value, a peak streamflow value, and I have a current precipitation value. And I want to know how important precipitation is to generating that value of streamflow. And we believe this to be a causal relationship. Precipitation goes through some mechanism and results in streamflow. But I have a context, which is how previously wet or dry the current system is. So I could have a situation where the system is so dry that the precipitation has no effect on the streamflow. Or I could have a situation where the system is completely saturated, and so the dependence of streamflow on precipitation is very strong. So in other words, sensitivity is mediated. I'm using the word sensitivity because I'm not clear if I'm using importance and sensitivity correctly. Clearly, precipitation is important to streamflow, but its importance is mediated by some other variable. And the degree of importance is context dependent. So I'm just curious how that plays into this, or is that another level of complexity above what you're looking at already?
yeah, so I think that would fit into the local data framework. And are you going to AGU?
Unfortunately not, no.
Oh, okay. Well,
why are you asking?
Because I think I have to answer that question at AGU. So we're submitting we're submitting an abstract for that I think answers that question. So
okay, well, hopefully I don't have to be at AGU.
I think it's to one of your sessions as well, so you'll see it early. I guess.
Okay, so when you're ready to talk about it, I'd be happy to hear about it.
Yeah.
Anybody else have discussion points, questions? Maybe you could say something about your strategy for approaching the local data issue then.
At the moment, I don't really have a strategy to do this. Okay. Like, as you can see from this table, no one does, and it's just kind of an idea based on this table because no one has done it.
Okay.
This table actually doesn't come from me. This comes from another paper published pretty recently, but yeah, I think it perfectly goes. I mean, I'm not sure how to do it more generally, but at least to answer the question that you just had, there definitely is a way. And yeah, you can come see my AGU presentation on it.
I know you said that you're wanting to explain an observation rather than a model output. But philosophically, we think of the process, the data generating process, as some representation.
Mhm.
And so, in a particular sense, there's no difference between a representation and a model, except whether the model is accurate or not.
Yeah, but the model's never accurate, so it's it's better
But-
just to look at the data itself.
But if you can think of it as a representation and assume that that representation, even if you don't know what it is accurate because it generated the data,
Yeah.
then what you're really asking is, what are the conditions that maximally explain that particular observation, right? Something like that.
Yeah, but if we had the data generating process in the form of some model, we can get, counterfactual information and
Right.
interventional information. So we wouldn't even, I wouldn't even ask that question. It's just go straight to the counterfactuals, Leila?
Yeah, hey Joseph, great presentation. I have questions. So I see how your method is um, highly dependent on how we can remove dependencies, right?
Yeah.
Between the different features. And so I was wondering if you have tested different pre-processing techniques, so that's the ones that you show here for the data. Yeah. In hydrological data, so that we can recognize how it's best to remove those dependencies. And I am asking this mostly because I don't know to what extent if you are able to recognize synergies, and maybe the synergies are being deleted somehow, which is very frequent when you use these techniques for hydrological data.
Yeah, so in the normal techniques that we tested, we can't actually remove synergies, but I think there are ways, we just haven't tested them yet. For Okay, so this is a plot from the paper where we're comparing linear regression with optimal transport. So this is the mutual information. We're just measuring it by how well we can predict each feature with the other pre-processed features. So the raw data is in black, so there's no pre-processing there. And then linear regression, you can see, is removing some of the dependencies. And then optimal transport perfectly removes the dependencies. So there's no mutual information anymore. And again, this is for the breast cancer data set. And this is kind of the other side of the coin. So we remember we have those three optimality conditions. The first, just it's a function of the original, which it always automatically satisfies. The second is it has to be independent of xi, so that's what this plot is showing. And then the third is the information loss one. So this is showing the information loss for optimal transport and linear regression. And actually, it's not, okay. Sorry, I kind of misspoke. So it's not showing directly the information loss, but it is showing how much we're transforming each variable. So these could be kind of imperfect, could be not one while still showing some information loss in this plot. Anyway, I also have a plot for hydrology. Okay, so you can see here, there's a huge difference, right? In the original in the breast cancer data set, these kind of dependencies in the raw data were all the way down at like 0.5 or something, so it's easier to remove. In this case, linear regression does terribly, can't really do anything. Optimal transport does pretty well, goes down to like 0.25 or something, but it doesn't get all the way down to 0. So there's still some dependence left that we weren't quite able to remove. But here are the results for, can't remember what variable this is. Let's see. I don't know. I think this is probably mean annual stream flow. So all these ones are giving mean annual precipitation and aridity as the most important features, and you kind of go down from there.
Yeah. Joseph, I am wondering, this goes into the local case issue, but if, for instance, you have the same data sets for two different locations and you want to compare how important, relatively important are those features across sites, will this give us like a good representation of how to differentiate those?
Yeah, definitely. So you can, the actual importance values are interpretable, I'd say. So they can be, I think, compared across data sets. So yeah, you can it's basically somewhere in between global and local. So you're just looking at the global importances across two different data sets, which you totally can do. Yeah. So you can, run UMFI on camels US and then run UMFI on camels Great Britain. And yeah, you can definitely see some differences there.
Yes, I think that is a good point because, yeah, I was wondering about the interpretability of the results because I noticed how the pre-processing steps for the method, it's gonna end up transforming the original features, right, into these new representations.
Yeah.
So it can be sometimes really hard to interpret the results, especially for hydrologists, unless you have a very clear understanding of the physics behind the process that you want to consider as a target, right?
Yeah.
So
yeah, the feature importance is just the difference between two evaluation functions or the universal predictive power. So as long as those evaluations are the same, yeah, so the evaluations are the same across the difference that you're making for one feature importance value. But then if you use the same evaluation metric for another data set, then they can definitely be compared. Yeah.
thank you, Joseph.
Any other last questions?
I guess I have one more that would just show my ignorance. But in a couple of the recent meetings, I've seen talks discussing shapely values.
Yep.
And all, like, very computationally oriented talks, like look at all these permutations we ran on our supercomputer and came back with these sort of relationships. How does these techniques that you're working on relate to that sort of work? Or, is it overlap? Are they making different assumptions?
Yeah, so the original MCI paper compared against Shapley values, and that's why we didn't, because they already compared against it themselves. And, obviously they compared against it and they found favorable results compared to that. I'd say in general, Shapley values will act kind of like permutation importance. Shapley values are very good for interpreting a model or interpreting kind of specific prediction. of a model. But again, it doesn't have these nice properties when you add correlated features that the importance stabilizes.
So when I see those talks, I should pull them aside and tell them to check out your work.
Well, not necessarily. I mean, Shapley values have a completely different goal. Like all these computer scientists who are making these methods, have their best intentions and are creating perfect methods for those intentions, but those intentions are completely different than the intentions of scientists. So if you see a scientist who's using Shapley values to say something about the relationships in their data, then yes, you should point it out. But if it's just method development, it's perfectly fine.
Yeah, that's the only way I've seen them used. So, okay.
Right.
Thanks for clarifying. I'll be sure to do that.
Yeah.
Do we have any last questions for Joseph?
I got a question, but generated by Timothy's last comment. This, for example, on Shapley values that the objective is, well, to understand this model, but how do we can modify those methods to get closer to our interest? For example, in these Shapley methods where we change predictors value to see how the outcome is affected. Usually those changes in the predictors is not restricted to physical conditions or how two variables will present at the same time or things like that. Can we not like modify the rules of Shapley modifications to match how the physical system will behave, and therefore like say, okay, we are not explaining only a model, but getting closer to trying to understand the system?
Yeah, so people have kind of tried to do that. So there's this paper called True to the Data versus True to the Model feature importance here. And I think they are the authors of some really famous Shapley works, and they do explain what they mean in the context of Shapley, but they're kind of very unclear about how they actually implement the true to the data scheme. And I'd say the only methods that so far exist for this explaining the data so far is MCI and ours. But yeah, I think the Shapley values really depend so much on the model that you can't really get away. It's very hard to get away from Shapley values explaining the model because it's so intertwined with the specific model. But if you want to read more, yeah, there's this paper. It's kind of hard to find, so just email me if you have trouble. But yeah.
Okay, cool. Thank you.
Thanks, Joseph. I'm going to have to go now. So that was a great talk. Appreciate it. What's the next one, Leela?
Yes, so we have in August 14, it's just per root. He will be talking about Bayesian, let me see, Bayesian frequentist uncertainty quantification.
Sorry, Bayesian what?
Bayesian frequentist uncertainty quantification under model misspecification.
Okay.
Yeah.
Sounds good.
Okay. Thank you so much. Thanks, Joseph, for the
Thank
great
you.
presentation.
Yeah, thanks for coming.
See you in 3 weeks. Bye-bye.
Yeah.
Bye.